Okay. So what I want to cover today is going to be the last topic for truss structures. And we're going to look at temperature changes. Okay. And we will start on page 313 of the reader. Okay. And so what about temperature changes? In your earlier courses, you've seen statements or you heard statements along the lines of, well, if the temperature of a body is increased, okay, the body gets larger, okay, increases in volume. Okay. And if the temperature is decreased, the body shrinks, okay, or decreases in volume. So first, let's try to quantify that, okay? And let's try to think about what this means in our situation. Okay? So imagine, right? And as before, we're going to work in a local coordinate system. Okay, we have our bar. We're going to pin it here. This is our node I. Okay. The usual properties E, A, and L, okay? And then we're going to introduce another property, coefficient alpha. We're going to call this guy a coefficient of thermal expansion. Okay, it will make sense in a minute, okay? Then we're going to denote the end node by J as usual, and we're going to put this guy on a roller. Okay? And so supposedly, let's denote by delta T, right? And delta T will be a temperature change in the bar, right? Relative to some ambient one, okay? Okay. So then, if you apply the temperature change, right, as you would expect, right, if the temperature is positive, right, the bar will change volume, okay? In our case, this is a one-dimensional object, so it will elongate, okay? So node J will go and move to some new location here, right? Because it can roll back and forth. Okay, and so this guy becomes, let's call it delta 0, okay? So how should we estimate delta 0? Okay, well, if we apply temperature change delta T, right, let's assume a simple model that the elongation of the bar will be proportional to the temperature that we apply, okay? So if it's positive, then it will elongate by something that is proportional to the temperature, right? So let's write delta T here, okay? Now, if you look at the bar of size L, for example, and bar of size L over 2, okay, you can imagine that a longer bar, if you apply the same amount of temperature change, will elongate more than a shorter bar, okay? So this dependence can be reflected by multiplying this by L, okay? And I think this is all the information we have at the moment, right? And so, you know, imagine putting yourself in the shoes of the experimentalist, right? You're given the temperature change, you're given a length, right? You sort of expect, or you run some, experiments, and you realize, okay, there is delta is proportional to delta T, is proportional to L, right? The only thing that's left is slap a proportionality coefficient here, alpha. Okay. Okay. And so we derived sort of this relationship. Let's put a prime here as well, because it's a local coordinate system, right? Delta prime 0, okay? And the relationship we get, right, the model that we have is alpha, delta t, and L. Okay. Another way to think about it, we can take and divide by L. You get delta prime 0 over L equals alpha delta t. Okay. So this is an interesting relationship because this guy expresses the elongation. Okay. And elongation, sort of, there's a length scale associated with it. Okay. And that length scale depends on, how big the bar initially is. Now, if you divide through by delta L, okay, this relationship here is a strain, right? We assume the strain is constant. And so another way to look at this, right, is the application of a constant temperature difference, okay, results in a constant strain in the bar. And the relationship between the strain and delta t is linear, and the proportionality coefficient is exactly coefficient of thermal expansion. Okay, gives a relationship between temperature change and strains developed in the bar. Okay. And so now you can see that this quantity is dimensionless. This quantity has units of temperature, right? So as a result, alpha has to be proportional to something over some units of temperature. And then you can choose to work in Fahrenheit, for example. Okay. Degrees Fahrenheit. All right. So at this point, right, then if we look in the local coordinate system, right, delta 1 prime, remember, delta 2 prime, delta 3 prime, and delta 4 prime, right? We see that in this situation, delta 1 prime is 0, right? Delta 2 prime is 0. I apologize. Delta 3 prime, okay, is exactly alpha delta t L, right? Or delta 0 prime, this elongation, and then finally delta 4 prime equals to 0. Okay, so we can take this state of the displacement, multiply by gamma RBM, right, times delta prime here, okay, and that we see that it's going to be exactly delta 3 prime minus delta 1 prime, okay, relative elongation, and that relative elongation is exactly delta 0 prime, okay, and we derived it to be alpha delta t L, okay. That also equals to, remember, delta prime over bar, basic displacement. So basic displacement becomes delta prime equals alpha delta t times L. Okay, and as a result, then basic force, right, due to the elongation, right, it was basic stiffness, right, times the basic displacement. Basic stiffness was EA over L, right, and the basic displacement becomes alpha delta t L. Another interesting fact, L cancels out, okay, and you get E A alpha delta t. Okay. And so this is the basic force, right, that is developed in the bar. Okay. Okay. So now, supposedly we keep the ends fixed, I and j, right? We apply delta t, Then we have our usual guys, EA, L, and alpha, right? But now we're going to fix them. Okay? So what's going to happen is the bar is going to try to expand. It cannot expand. It will develop internal forces, right? Internal forces will be of magnitude EA alpha delta T, okay? And they will be compressive, okay? And this puts us in the same situation as a distributed load, right? So remember, when we apply the distributed load, we assume that the nodes don't move, okay? And the distributed load introduced, some form of end node forces, okay? So you think of the temperature change, right, along the same terms, okay? Temperature change will introduce the end node forces, and the end node forces, the magnitude, right, becomes EA alpha delta T, right? And these are distributed in a constant fashion, okay, over the bar. Okay? So then in that case, right, how do we model loads? Right? We say, okay, for a given element in the basic coordinate system, right, because now basic forces make sense, right? We're going to decompose the force into K prime for that element times delta prime over bar, right, for that element, right, which would be the forces that are coming from the displacements. And to that we add, right, F prime F 0. Okay. In this case, there'll be forces coming from thermal expansion or from application. Temperature change. Okay. Right? And the key is that relationship actually holds in the basic system. Right? And so because the forces are compressive, what you see is that F prime F0 equals exactly minus E A alpha delta T. Okay. And so in the local coordinate system, okay, this relationship is reflected as follows. Right? So F prime for element E, okay, vector in the local coordinate system, is obtained by taking kappa prime for element E multiplying by delta prime, right, which will be forces that are coming from end node displacements in a local coordinate system, plus F prime F for element E, okay, and then F prime F for element E for the case of the application of the temperature change, right? You look up, okay, and you directly read it off of this force diagram. Okay? In the first slot, you get EA alpha delta T, right? Forces, the corresponding vertical force is 0, right? Because the bar is trying to elongate in the axial direction. There's no vertical action for trusses, right? Then here you get minus EA alpha delta T, right? That's the compressive contribution from the negative force, right, at node J. And then you get a 0 in the vertical direction. Okay. And now that you have that, your analysis proceeds as before, right? You set up a system KFF UF equals to PF, right? You subtract PF0, right? These are the forces that are coming from distributed load, including temperature load. And then you assemble PF0, right? Assemble element by element, like you do everything else. you assemble this guy element by element, okay, from thermal loading contributions. Okay, so next what I suggest we do is take an example to see exactly how this works. Also will give us an opportunity to examine sort of a structure with a different geometry. Right? So what I want to go do next is go through the example on page 316, okay, of the reader. And again, we have a fairly simple structure. Okay. We have 3 supports like this. Okay. The distance between the supports is 12 feet. This way. Okay. And then we put together a structure that connects the 3 supports, right, with some sort of apex node at the top. Okay. And this distance, vertical distance, the height of the structure is going to be 16 feet like this. Okay. So let's give this node label 1. This becomes node 1, node 2, node 3, node 4. Okay. And then let's label our degrees of freedom, right? We'll go through the free nodes first, right? So it makes sense to label x displacement here by u1, the corresponding nodal force by p1, right? This becomes u2, the corresponding nodal force p2, okay? And then we go to the restrained nodes and use up the rest of the DOFs, right? u3, p3, u4, p4, u5, p5, u6, p6, u7, p7, right? And u8, p8, okay? So you're looking at a situation where you have 4 nodes, right? You have 8 degrees of freedom. Only u1 and u2 are free degrees of freedom, and the rest are restrained. Okay. So let's give the problem some additional dimensions, right? Let's assume that this is our element A. Okay. Right. And its cross-sectional area is going to be 8 inches squared. Okay. This is element B. Let's assume its cross-sectional area is 6 inches squared. And this becomes element C, also with a cross-sectional area of 8 inches squared. Okay, so it looks like a nice symmetric structure. Right? We're going to assume that these are all bars that are made of the same material. Okay, and Young's modulus for all the bars is the same. 29,000 kilopounds per square inch. Okay. And finally, the coefficient of thermal expansion, alpha, we're going to set to something like this. It makes sense, at least for these dimensions, right? 6.5 times 10 to the minus 6, and this is 1 over degrees Fahrenheit. Okay. And so now we haven't talked about the loads, okay? So let's assume the only load that's acting on the structure, okay? So basically loading. And that load consists of a temperature drop of 30 degrees Fahrenheit in member A, okay? So, I mean, suppose that this sort of is something representative of a, greenhouse or something like that, and the element A is the side that's exposed to wind, okay, for example. And this kind of icy wind comes and brings a drop of 30 degrees. Yeah, just okay. So we have element A subjected to temperature loading of 30 degrees Fahrenheit, okay, which is not much, okay, and so your goal is to just resolve the structure. So we compute the deformation, okay, and let's look at the element forces. All right. So then what do we know? All right. So U is comprised of two parts, UF and UD. Okay. UF are our displacement unknowns, U1 and U2. Okay. These are free DOFs. Okay. This is what you're going to find. UD are the rest of them, right? U3, U4, U5, U6, U7, and U8. Okay. These are restrained DOFs. Okay. They don't displace, so you get a vector of zeros, 2, 3, 4, 5, 6. So this makes your problem quite a bit simpler. Okay. All right. So what do we need to do next? All right, next we need to build KFF. Yeah. Structure stiffness matrix, okay? And then we go from elements 1, 2, and 3, okay? Let's start with the element A, okay, or ABC. Right. So next is we're going to decide what the element orientation is, right? And I claim that going this way for each element is going to be the easiest thing. Okay. So if we look at the element orientation, right, then node I is node 2 and node J is node 1. Node I is node 2 and node J, right, is node 1. The beginning and end. Okay. Next, right, so length we can compute to be 20 feet. Okay. Simple sum of squares, square root. Okay. However, all the problem dimensions, right, and material parameters are given in terms of inches. Okay. Like the area is in terms of inches squared. Young's modulus is kilopounds per square inch. So we need to go ahead and convert this to inches. So we take 20 feet, multiply by 12, we get 40 inches, 240 inches, right? Cosine phi, right, is delta x over L. If you look at the geometry, is 12 over 60, or 12 over 20, or 0.6. Okay. Sine delta y over L, right, this becomes 16 over 20, and this is 0.8. Again, sort of deliberately choosing the dimensions such that the hand calculations are not so crazy. Okay, basic stiffness EA over L for that element becomes 29,000, right, times 8 inches squared divided by the length of 240. Okay, we get 967 kilopounds per inch. Okay. The element stiffness matrix, let me just go directly to the global coordinate system. Right? Recall, this is gamma ROT for element A transpose, gamma RBM, right, transpose times the basic stiffness for element A. Okay. This is exactly 967 that we computed before. Okay. This is gamma RBM and gamma ROT for that element. Okay. So I presume you can carry out the calculation on your own. Okay. And you get a 4x4 matrix. Okay. And that matrix in principle will be fully populated. Okay. However, in order to avoid much writing, right, let's see. So for this element, right, if you look at element A, the local displacements are restrained at node I, right? So the entries of the ID array are going to be zeros, right? And then the 3, 4 displacements point to 1 and 2, okay? And so if you write down the ID array on top of the matrix here, right, and on the side, you're going to get 0, 0, 1, 2, right? And likewise, 0, 0, 1, 2, okay? This is the ID for element A. Okay? So as a result, you don't particularly care about the entries here, here, or here, right? All you care about is this lower 2x2 block. Okay? And so if you carry out the calculations, you will find that the numbers in that block are 348.12, 464.16, 464.16, it's symmetric. Okay, and 618.66 is 88. 618.88. Okay, and so all these units are in kilopounds per inch. Okay, just make sure your units are consistent. Okay, good. All right, so let's go to element B. Okay, and I'll go quickly. Node I is node 3. Node J is node 1. Okay. Length is 16 feet, right? Cosine phi is what? Delta x over L. Okay, just use that definition. Don't try to come up with your own angles and right-hand rules, left-hand rules. That's it. Once you decide what your starting and end node are and the corresponding coordinates, everything is defined. Okay, you don't need to worry about which way the angle goes. Cosine phi equals delta x over L, right? Delta x is 0, L is 16, you get a 0, right? Sine is delta y over L, right? Delta y is L, this is 16 over 16 equals to 1. Okay. And so this defines for you the entries of the rotation matrix. Okay. Okay. Then we carry out the basic stiffness, EA over L, right? 29,000. A is 6, L is 16. Okay. You end up with 906, right, kilopounds per inch. Okay. And so once you do that, then the corresponding global matrix, so element matrix with respect to global coordinates, right, becomes, right, you use the usual expression, you end up with something that's 4x4. Okay. I suggest again to avoid some, you go look at the at element B, right? You can see that the first 2 degrees of freedom are going to be restrained, right? And the second point to 1, 2 again, right? Which allows you to basically write down ID array here, ID array there, 0, 0, 1, 2, 0, 0, 1, 2. This is ID for element B. Okay. So again, you don't care so much about these 3 blocks. Just try to populate this one. Okay. And you see that this is 0, 0, 0, 906, which is not surprising because the element is aligned with the y coordinate system. Okay. Finally, let me take you through element C and everything is more or less the same. Okay. Right. Node I is node 4. Node J is node 1. Okay. The length is 240 inches. Okay. Now, cosine phi equals 2. Again, you just apply the definition, delta x over L. Okay. All right, let's go and see what delta x over L is from the picture. Okay. Delta x is, you go from node 4, right, that's your x coordinate, to node 1. So the x coordinate will be here. So you actually go in the negative direction, right? So your delta x becomes minus 12, okay? And the length is 20. So I get minus 0.6, okay? So don't be afraid, right? If your cosines have negative numbers in it, it's perfectly fine. Sine phi equals delta y over L. Okay. The y elevation is still the same, 16 positive, divided by 20, you get 0.8. Okay. So use this to populate the ROT matrix, okay, which looks like right, minus 0.6, right, 0.8, minus 0.8, minus 0.6, 0, 0, 0, 0, 0, 0, 0, 0, and then the 2 by 2 block repeats. Minus 0.6, 0.8, minus 0.8, minus 0.6. Okay, so this ends up being, right, gamma ROT for element C. Okay, again, don't worry about the angles, just straightforward application of coordinate differences. Okay. So when building the matrix, okay, nothing new, use the usual expression, equals to, you come up with something that's 4 by 4, right? You put the ID array, and again, the way we set up our elements, right, and our orientations is we start here, right? The two nodes are restrained, so 1 and 2 are restrained. 3 and 4 point to 1 and 2. That defines for you the ID array, which again happens to be 0, 0, 1, 2, okay? Because of the way we chose to number our nodes and define element orientations. Okay? So again, you don't care so much about this, this, or this, right? You just care about the bottom block, and the bottom block ends up being 348.12 minus 464.16 minus 464.16 and 618.88. Okay, good. All right. So next, right, we'll go through the elements one by one, right, and we assemble these, right, into entries of KFF, right? So this guy will go into 1, 1, this guy will go into 1, 2, this guy will go into 2, 1, and this guy will go into 2, 2. Right? So if we look at the structure of KFF, it's going to be a simple 2 by 2 matrix, right, like that. Okay. And so from the first element, we get 3, 4, 8, 12, 4, 6, 4, 16, 4, 6, 4, 16, and 6, 18, 88, okay, from the first element. Right, from the second one, this is 0, this is 0, this is 0. Only K22 entry will be added to 906, right? So 0, 0, 0, right? Plus, 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 plus 906, okay? And from the third element, right, We add 348 here. 12. We add minus 464.16. Right. We add minus 464.16. And from this one, we add 618.88. Okay. And so when we do the final computation, right, we get a beautiful diagonal matrix that looks like this. Okay. 696.24. 0, 0, 2,143.76. Right, and all the entries are in kilopounds per inch. So what does that tell you? Right, this structure of the stiffness matrix perfectly reflects, right, the symmetry of the problem. Okay, meaning, okay, if you apply if you look at the structure here, right, the stiffness matrix is diagonal, okay, which means if you apply the force in the direction u1 and not in the direction u2, right, then the corresponding displacement will only be in the direction u1. Okay? If you apply force in the direction u2 but not u1, the displacement will be only in u2. Okay? So there's no coupling between horizontal and vertical action. And this lack of coupling comes from the fact that your your structure is symmetric, right, around this axis here. So this structure of the stiffness matrix, right, reflects symmetric structure of your structure, I guess. All right. Good. Okay. So we have KFF. Right. We got it. We want to solve for UF. Right. That guy will be PF, which is 0. Okay, we're not applying any nodal forces directly. And minus P of 0. So this is the only remaining thing that we need to calculate. Okay, and so P of 0 in principle, right, will have contributions from A, B, and C. Right. Let's look at the contribution A. All right, and we can look directly in the local coordinate system. Okay, and we get E. A alpha delta t, right? What we derived earlier in the lecture, 0 minus EA alpha delta t, 0. Okay. Now, so here we need to plug in 29,000, right? For A, we need to plug in 8, right? For alpha, 6.5 times 10 to the minus 6. And for delta t, right, remember, we're dropping the temperature, so this becomes minus 30. Okay? So because of that, this vector becomes minus 45.24, 0, 45.24, 0. Okay. From there, remember, we go to the element force in the global coordinate system, right, by taking gamma ROT for element A transpose, right, times F prime F for element A, right, that we derived. Okay. And so if we do the calculation, we get minus 27.144, 36.192 minus, and then positive 27.144 and 36.192. Okay, so this is what this product will give you. So for that element, the ID is what? 0012. Right? So this entry will go into PF0, 1, okay? And this entry will go into PF0, 2, okay? Okay. In addition, you see that no loading coming from elements B and C, right? So there are no distributed loads, and the temperature load is only applied to element A. Right? So in this case, right, our PF0 simply becomes the last two entries of this vector, right? 27, 144, right? And 36, 192, okay? And the forces in this case are always in kilopounds. So then we solve for UF equals to KFF inverse PF, which is 0, minus PF0, which we just derived from here, right? So we get $696.2400 $2,143.76 minus 1, right, times minus 27,144, 36,192. Okay. And if we work out the end result, okay, we get minus 0.0390 and minus 0.0169. Okay? Right. So you can see that if you started out with a structure that looked like this, all right, in the exaggerated view, this node moves to the left about twice as much as it moves down. Okay? So it's now here, and this becomes the displaced configuration. Okay. What also do you notice, right? Well, sort of everything for that structure was quite realistic, right, in terms of dimensions, material parameters, cross-sectional areas, and application of temperature, right? And so what you see is the amount of displacement is actually quite small. Okay. Well, you're not surprised, right? I mean, when you expose, you're at your house or something is sitting outside for a while and cooking, and you get a 30-degree temperature hike, you don't see the structural deformation really with your own eye, okay? And so this is, these type of deformations are quite realistic, okay, for these type of structures subjected to that type of thermal loading. All right, and so the last remaining bit is we see the deformation, right? Let's look at the element forces. Okay, so if we look at the element forces, we see that delta A, okay, we extract from the global 0, 0, U1, U2, okay. Then we can compute the basic displacement, delta prime, okay? And this is going to be gamma RBM times gamma ROT for element A times delta A. Okay, so if you carry out the calculation, right, you get minus 0.0369. inches. Okay, so that element shortens by a small amount, right? So what are the forces that are developed in that element? Okay, well, it'll come from two sources, right? It comes from the shortening first, okay? A, delta over bar prime A, right? And then from the application of the temperature load, F prime, for that element, F. Okay? And here we get 967, right? That was the basic stiffness, times what we just computed, minus 0.0369, okay? And to this we add 45.24. So if we do the calculation, okay, we get 9.56, okay? Right, so it's interesting. The element shortens, right? However, the force inside of it stays positive. Okay? And so you see the competition, right? It shortens, so it tries to be in compression, okay? But then there's enough temperature drop to keep it in tension, okay? So it's tension, despite shortening, okay? So kind of an interesting situation, okay? Now if you go through element B, okay, you get the same thing, right? You go through the motions, right? You find that the basic displacement there, prime B, okay, becomes minus 0.0169, okay, also shortening. Right. But the basic forces, F prime B, right? You take kappa B times delta B, okay? You end up computing 906 stiffness, right? Times minus 0.0169, okay? Then you're going to add the temperature change, but that is 0, okay? So we don't care. So at the end of the day, you end up with a compressive force of minus 1531, okay, kilonewtons. And here, because there is no temperature load, shortening leads to compression, as you expect. Okay, and then I'll let you conclude. See on your own. Okay, and this concludes our lecture set on trusses. Okay, and then we're going to start with beam frames.